Next, we can discuss the pH scale. pH refers to the concentration of hydrogen ions in a solution. A solution's pH is the negative base 10 logarithm of the hydrogen ion concentration, annotated by H plus here. You don't have to memorize that, but as an example, a pH of 4 solution has a hydrogen ion concentration that is 10 times greater than that of a pH 5 solution. That is, a solution with a pH of 4 is 10 times more acidic than the pH 5. The pH scale consists of a series of increments ranging from 0 to 14. A solution with a pH of 7 is considered neutral, neither acidic nor basic, and that's what pure water is, pH 7. The lower the number, below 7, the more acidic the solution, or the greater the concentration of hydrogen ions. The concentration of hydrogen ions at each pH value is 10 times different than the next, so going from 6 to 8 is 100 times different, if that makes sense. Acids and bases dissociate in water into electrolytes. Acids release hydrogen ions into solution. Strong acids release all of their hydrogen ions, or most of them, into the solution, and that's kind of like hydrochloric acid, which is a stomach acid. It releases all those hydrogen ions in the stomach's watery environment. This strong acid helps degrade food material and kill ingested microbes. Weak acids don't release all their hydrogen ions. Some remain bonded within a compound solution, just like vinegar. Bases release hydroxide ions into solution, or accept hydrogen ions that are present in an acidic solution. These hydroxide ions combine with present hydrogen ions to form water, reducing the acidic solution. Strong bases release all or most of their hydroxide ions, while weak bases only release some of those hydroxide ions. So, an acidic solution has a higher concentration of hydrogen ions than hydroxide, and basic solutions have the inverse, while neutral solutions have equal concentrations of hydrogen and hydroxide ions because all of them are moved together. They're all water, H2O, equal. So now we got to be able to control those pH levels in the body, homeostasis. The pH of human blood normally ranges from 7.35 to 7.45, although it is typically identified as pH 7.4. At this slightly basic pH, blood can reduce the acidity resulting from the carbon dioxide that is constantly being released into the bloodstream by the trillions of cells in the body performing cellular activities. Homeostatic mechanisms, along with exhaling CO2 while breathing, normally keep the pH of blood within this normal range. This is critical because fluctuations, either too acidic or too alkaline, can lead to life-threatening disorders, such as pH going below 7.35, entering the body into acidosis, which depresses the central nervous system. The opposite happens when pH goes into above 7.45, the body enters alkalosis, which overexcites the central nervous system. All the cells in the body depend on homeostatic regulation of these acid-base balance at a pH of approximately 7.4. The body therefore has several mechanisms for this regulation involving breathing through the lungs, excretion of chemicals in the urine by the kidneys, and internal releases of chemicals collectively called buffers into body fluids. A buffer is a solution of a weak acid and its conjugate base. The buffer can neutralize small amounts of acids or bases in body fluids. For example, if there's even a slight decrease below 7.35 in the pH of bodily fluid, the buffer in the fluid, in this case acting as a weak base, will bind to the excess hydrogen ions. In contrast, if pH rises above 7.45, the buffer will act as a weak acid and contribute hydrogen ions. One example is the bicarbonate buffer system. When food is mixed with hydrochloric acid from the stomach, this would burn the small intestine, which is the next portion of the digestive tract after the stomach. If it were not for the release of bicarbonate, a weak base that attracts hydrogen ions, bicarbonate accepts some of the hydrogen ions, thereby reducing the acidity of the solution. So again, pH is crucial for maintaining homeostasis. Next, we can kind of look at the importance of water. It keeps our body temperature normal. It provides good protection for our cells. which are mostly made of water, and it provides a cushion for our cells. We can see this in people's faces when they're dehydrated. They sink in a little bit, they're not as plump. We need water for all the chemical reactions to occur in our body. They're an excellent solvent and a base for reactions to occur. It allows the reactions to dissolve and interact because it is this great solvent.